Thank you very much for the introduction, and thank you for giving me the opportunity to present this work, which is joint with my advisors, Pierre Verhès, who is here, and Pierre Venave, who is not here. And it's indeed going to be about computing periods of projective hypersurfaces via effective homology. And so if you do not know what a period is, for the sake of this presentation, you can simply understand them as some integrals of rational fractions, such as the one presented here. So you set yourself some polynomial p, which defines some smooth hypersurface, and then you look at some rational function, a over p to the power of k, which is homogeneous and which has some degree condition, so that the whole integrand has degree 0. And you want to ask what is the value of the integral of this of this integrand on some cycle. So the cycle has to be something that avoids the singular locus of this rational function. And which has no boundary. And you can think of it just as a domain of integration of this integral. So this is a very explicit description of what a period is, but you can also understand it more intrinsically with regards to the surface x. Namely, if you're given some smooth projective surface, you have the singular homology of the surface, represent hn of x, and you also have on the other side another invariant, which is the algebraic theorem cohomology space, which is this one here. And so the singular homology sort of describes the topology of your hypersurface, whereas the algebraic theorem cohomology describes the algebra of this surface. But the theorem tells you that these spaces are isomorphic or dual to each other, and this duality is given by some integration pairing. So you can take some form, some element of this cohomology, a form, and integrate it on the cycle, an element of the homology. And so this duality is encoded in the matrix that represents this integration pairing in some given bases for homology and cohomology. And so the entries are called periods, and the matrix itself is called the period matrix of X. And the goal of what I'm going to talk about in this talk is to give some way to compute numerical approximations of these integrands, of these integrals, given just the defining polynomial of some smooth projective hypersurface of some projective space. Why would we be interested in computing this period matrix? I'm going to give two motivations. The first one is the fact that this period matrix describes a lot of the geometry of the variety, which can be seen by what are called Torelli-type theorems, which tell you that if you take some classes of varieties, for instance, K3 surfaces, if you manage to prove that two K3 surfaces have the same period matrix, without going into the details as to what this means, then you will have shown that these two K3 surfaces are isomorphic to one another. And in fact, if you manage to compute sufficiently precise numerical approximation of this period matrix, you can recover some algebraic invariants, or you can hope to recover some algebraic invariants of the varieties you're considering. The second motivation comes from physics and concerns Feynman integrals, because periods arise as Feynman integrals, which are integrals associated to Feynman graphs, which arise as scattering amplitudes in quantum field theory. And what this means is that it allows physicists to compare their theories to actual experiments led in particle colliders. For instance, the graph that you have here represents the discovery of the Higgs boson. So you have two curves, a green one and a red one. The red one has some sort of bump, and it corresponds to a model with a Higgs boson, while the green one corresponds to a model of physics without the green one. And then the black dots here are measurements that were led in the Large Hadron Collider. And so the presence of this bump in the measurements tell you that indeed there is a Higgs boson, and this bump is actually called the Higgs bump. Okay, so this was motivations, and now let me mention a few lines of work which go into, well, which try to compute these periods for certain cases of varieties. The first one is the case of algebraic curves, which was extensively studied because it coincides with the case of Riemann surfaces. And so there are these papers and more that that try to provide algorithm, well, that provide algorithm for computing these periods. But in the case of Riemann surfaces, this is the same thing as computing Riemann matrices of these Riemann surfaces. In higher dimensions, there are two papers which deal with the case of some higher dimensional varieties, namely double covers of some projective space ramified along some union of hyperplanes. So these are these two papers by Alessandro and Janel and Sink and Van Straten. And the final line of work, which matches, well, which is the closest to the work I'm going to present afterwards, is the work of Emre Sertoz, where he provides an algorithm for computing the periods of hypersurfaces of any degree, any dimension in generality, as long as it's smooth. And I will detail in the next two slides how he does this. And I will, well, I will illustrate it on this example. Let's say we wish to compute this integral here for some given cycle gamma, and we consider this rational function here. To compute this, instead of directly considering just this number, we introduce some parameter, and which turns this number, well, this integral into some parameterized integral. So we add just some t in front of the last monomial here. And the reason we do this is because with this new function pi, if we set t is equal to 0, then we see that we have something very symmetric. We have x cubed plus y cubed plus z cubed. And this is the Fermat elliptic curve, and we have exact formulae for the periods of the Fermat elliptic curve. So we know the values of pi of 0. So this is the first element of this method. And the second one is that we can actually compute some differential operator that is satisfied by pi of t, which is just shown here. So this differential operator sort of encodes the deformation of the variety as t varies, and it's called the Picard-Fuchs equation of this family of varieties. And so the point is that because we have the value of pi at 0 and this differential equation, we can numerically compute the analytic continuation of pi along some path which connects 0 to 1. And doing this, we can obtain the value of pi at 1. And this is precisely what we were after, because if you set t is equal to 1, you recover the initial number we were after. And this we can do effectively thanks to methods developed by these people, so Chudnovsky, Van der Hoeven, and Mitsaroba. And we can recover numerical approximations of these periods with rigorous error bounds and with very high precision. One issue, however, is that the understanding of the cycle we have here is not very explicit. It's given as the deformation of the cycle we start with at the Fermat variety. So we understand the cycle of our variety as some deformation of the cycle in the initial, well, in the Fermat variety. But however, this method still works in all dimensions and in all degrees, so it sort of solves this, this question, except that from an effective point of view, it's not sufficient because it has these two drawbacks. Well, the first one is the fact that this only applies to hypersurfaces because we need this Fermat variety or starting point where we know the periods, and this requires work. This is work that had been done by Frédéric Pham and Emre Sertoz. Well, Frédéric Pham in 1965, and later Emre Sertoz did some additional work in this regard. But so in general, if we consider other types of variety, for instance, complete intersection, we might not necessarily have this data, these starting points. And the second problem is that the differential operators, these Picard-Fuchs equations that need to be integrated, their size quickly gets out of hand as you increase the degree and the dimension of the varieties. And so, and in particular, they go beyond what we can do in terms of numerical integration with current software. For instance, to compute the periods of some smooth quartic surface in P3, you would need to integrate some operator of degree 21 and of very high, of order 21 and very high degree. Depending on the surface, it might be manageable, but in most cases, for quartic surfaces defined by generic polynomials with coefficients in front of all possible 35 monomials, this is not doable. And so one of the reasons why we have these two problems is because the description we have of these cycles is as a deformation of the cycles of another variety. So instead of building up these integrals from the ground up, we're deforming them from another variety. And also we do not have this description of the cycle which is effective enough to compute the integrals. And the hope is that by giving some more intrinsic description, we will be able to compute these integrals from the ground up and thus recover the periods of hypersurfaces in a faster way. And this is exactly what I'm going to present in the next slides. And let me first list a few contributions that stem from this approach. So first, we obtained this new method for computing periods with high precision. It comes with an implementation that you can use in stage math. So it's this package, Lefschetz family. You can try it right now. If you want to use this and have some trouble, please let me know. I will gladly help you set it up. And so this method is sufficient to tackle new varieties that were not attainable in reasonable time by the method of M-Hauserters, namely generic quartic surfaces. These quartic surfaces defined by dense polynomials that I've mentioned. The method I'm going to present allows you to compute them on a laptop in roughly an hour, in most cases. A byproduct of this method is that you obtain a description of the homology of complex varieties, which is interesting on its own. And finally, it's also generalizable not just to hypersurfaces, but to other types of varieties, so complete intersections, and some varieties with isolated singularities, for instance, also for for elliptic surfaces, this method works and also has an implementation. Okay. So now let me start with the case of curves. So again, this is not the new part, but the reason why I want to talk about the case of curves is because it's a nice introduction, and the algorithm I'm going to present is a generalization of this case of curves to higher dimensions, so I want to go over it. And I want to, well, I will illustrate it on this example. So let's say we want to compute the periods of this elliptic curve defined, so this is the Fermat elliptic curve in the affine setting. And what you are looking for here are one cycles of this elliptic curve. So you want to have some understanding of what the one cycles are, and this way you will be able to integrate on these one cycles. And one cycles, you can understand them just as loops in the elliptic curve up to some deformation. And so the idea is that you take your elliptic curve, you project it onto the projective line, and then so you project it via this map, for instance. And then the observation is that if you have a loop in the elliptic curve, the image of this loop in the projective line is going to be a loop in the projective line. And the question is, can you go the other way? Can you take a loop in the complex plane and lift it up into a loop of your elliptic curve? And to understand if this is possible, it might be wise to first not necessarily look at loops, but at paths in general. So the question is, I have a path downstairs, can I always lift it into a path upstairs? And for this, you look at what the fiber above a given point downstairs is, and the fiber is going to be, so the fiber is y over 2x plus 1 is equal to t, so y is equal to t times 2x plus 1, so you just replace y by this in your polynomial equation, and you realize that the fiber is precisely 3 points, the fiber here, so here t is fixed, 3 points parameterized by the roots of this polynomial equation of degree 3 in x. And as long as you avoid some bad values of t, so values of t for which this polynomial will have double roots, you will always have 3 distinct points that vary continuously with the parameter t. And so this means that if you take a path downstairs that avoids these critical values, these red points, and you pick some starting point upstairs, there is a unique way to lift such a path into a path in the elliptic curve that starts from this point. So now we can go back to loops and try to understand when can we lift a loop. So a loop will be lifted into a path via this construction, and the question is this path going to be a loop as well in our elliptic curve or not? And the answer is, well, not always, because if you start from a point here and you try to lift this loop, for instance, this point will move around, and when you go back to the initial fiber, it might have changed. So the point is that this loop downstairs induces some monodromy action on the points of the fiber. So it induces some permutation of the points of the fiber, which is called the monodromy action. And so this is an actual example. Well, this is a representation of the roots of the actual example of the elliptic curve that I shown in the previous slide. And another point is that if you take a simple loop around one single critical point, this permutation cannot be anything. It has to be a transposition. So precisely 2 points get permuted with one another, and the rest are fixed. And now if you try to lift such a loop, if you start from one of the points that does not move, clearly this provides a loop in the elliptic curve. But because downstairs this path is contractible, the path upstairs will be as well. So the homology of the loop you obtain here will actually be 0, so this does not interest you. On the other hand, if you start from another point, you will get something which will have some border, but nonetheless, it will have non-trivial homology class in the homology of the elliptic curve relative to this fiber here. And so per critical value, or rather per simple loop around a critical value, you have a unique such non-trivial homology class, which is called the thimble above the critical value. So it is this short path which has some boundary in the fiber. For instance, delta 1 here corresponds to the loop L1. And thimbles are very nice because they can serve as building blocks for the actual homology of the elliptic curve. Namely, if you take several thimbles, for instance, here, if you take the sum of delta 1, delta 2, and delta 3, you can see that their boundaries cancel each other. And so when you take that union, you get an actual loop in your elliptic curve, and thus you get an actual one cycle of your elliptic curve. And concretely gluing them together just means taking the kernel of this boundary map that goes from the thimbles to the points in the fiber. And the point is that if you do this, you can actually recover the entirety of the one cycles of your elliptic curve. And this is the example of one elliptic curve. This remains true for any algebraic curve. There's a slight twist, however, which is that some combination of thimbles are trivial. Namely, because we work in the projective setting, if you take a loop that goes around all the critical values, then this loop will be contractible in the projective line, like here. So this orange loop is contractible at infinity somewhat. So there are some combination of thimbles that are trivial, but you can compute them nonetheless, and you can recover them exactly. And thus, and if you cancel all these out, it turns out that these are the only trivial combination of thimbles that have no boundary in the homology, and you can compute them, and thus you can recover basis of the homology. And this provides you some algorithm for computing the periods, well, the homology and then the periods, which goes like this. First, you choose your projection, you'll compute these critical red values, and you compute simple loops around each critical value, represented in orange here. For each simple loop, you compute the action of monodromy. So this you can do in the case of curves simply by computing, by tracking the roots of this polynomial that defines the points in the fiber. Once you understand the monodromy, you have some understanding of the thimble, and more importantly, you have some understanding of the border of the thimble, because the border of the thimble is precisely the difference between the 2 points that get permuted. And once you have all the thimbles, you glue them up together using this, and you cancel out by these trivial combinations of thimbles, and in the end, you get some basis of the first homology group of your algebraic curve. And let me remind you that the goal was to compute periods of this algebraic curve. And this description of homology is very nice for computing periods, because we have an explicit description of these one cycles, some explicit, parametrization of these one cycles given by paths in the complex plane. So all we have to do is compute some line integrals, and this we can do using the numerical, the analytical continuation software that I've mentioned previously, and thus we can recover very high precision numerical approximation of these periods. So let me give you some example of this at work in the same case as the elliptic. Okay. Right. So this is this Lefschetz family package I have talked about, and I'm going to showcase it to you on the same example of the Fermat elliptic curve, so here defined in the projective setting here. And so I pick some fibration. This is the same projection to the projective line, so you see that y is sent to 2x plus z times t, which is the same thing. I pick some base point, which is not a critical value. So here is a representation. The red points are these critical values, and the green point is the base point. And for each critical value, I compute such a simple loop represented as, as this path in the complex plane. The fiber is the roots of these polynomials, so it corresponds precisely to 3 points. Thank you. And I represent the points in the fiber just as these 3 vectors. So this is the 0th homology group of the fiber. And then I can compute these monodromy matrices, which will just be permutation matrices. So these are the permutation matrices that corresponds to the simple loops around each of these critical values. So this is the first critical value, the second one. And as you can see, these are indeed not any permutation matrix, but transposition matrices. The border of the thimbles are given just as the difference between the 2 points that get permuted. For instance, for the first matrix here, the first and last point get permuted, and the border of the first thimble is this, and the first minus the last point. And then you can compute this kernel, so glue the thimbles back together to obtain actual homology classes in the elliptic curve. Then there are these trivial loops that I've mentioned, which you can compute explicitly. They are given here. So these corresponds to, let me mention this. So this vector corresponds to a combination of thimbles. So this tells you that you have to take the first thimble and remove the penultimate thimble, and this will give you a homology class in the elliptic curve. And similarly, here you have to take the sum of thimbles with these coefficients, and this gives you these trivial combination of thimbles that lie in the elliptic curve. And when you quotient the space generated by this, which has rank 2, because you can see that the sum of all these 3 is actually 0, so you quotient this space, which has rank 4, by this space, which has rank 2, you recover a basis of the homology of your elliptic curve, which, as expected, has rank 2. And then you can understand a basis of, this basis as lifts of these paths. So I know that I can lift this path to a non-trivial homology class in my elliptic curve, and then the second is just this one. And this gives me a basis of the homology. And then if I want to compute the periods, I just have to integrate this differential equation on this path. And in the end, I recover, it should take 5 seconds. I recover this period matrix, of which the entries are of transcendental nature. And so I have them with very high precision, so 300 digits roughly. And it's a 2 by 2 matrix, which characterize this link between the topology and the algebra of the elliptic curve.
The yellow segments are the Voronoi boundaries?
Yes. Precisely. I mean, it could be anything. All that matters is the path up to homotopy. But in this case, for numerical reasons, it's better to take paths that lie around these Voronoi boundaries. Yeah. OK, so this concludes the case of curves. Let me share my slides again. OK, So this concludes the case of curves and provides an algorithm for computing the periods of algebraic curves. Again, this was already known, this is nothing new, but the new part is what comes next, is the fact that you can generalize this method to higher dimensional varieties. And I'm going to talk about surfaces, but really this method generalizes further than just surfaces in any dimension. And so the idea is roughly the same. For surfaces, you're no longer looking for one cycle, but for two cycles. And two cycles you can understand as sub-manifolds of real dimension 2 of your variety. And one way to obtain such a thing is to consider some projection of your surface onto the projective line. And then the fiber is no longer going to be given by a finite set of points, but it's going to be given by some algebraic curve. And then to obtain a two cycle, what you can take is take some one cycle in the fiber and sort of deform the fiber along some path. And this green one cycle gamma is going to cut out this tube, which are represented in pink and called tau. And you hope to recover the two cycles of your surface by doing this, by taking one cycles and extending them along paths in the projective line. And the reason why this would be nice for computing periods is because of this formula here. If you try to integrate some function on, or rather some form on tau, you can do this in two steps. The first one being integrate the form onto gamma. And this is just some periods of some algebraic curves. I've already told you in the previous slides how you can do this. And then the second step is taking this line integral along L. And once again, you can do this using numerical analytic continuation software. OK, so now let me draw some comparison with dimension 1 to see what sticks and what's different. So in dimension 1, we were looking for one cycles. Now we're looking for two cycles. Thimbles were obtained as extending some points along a path in the projective line. And now we also have a notion of thimble, which is the extension of now a one cycle along a path, along a simple loop around one critical value. The monodromy was given as some permutation of the points of the fiber, which you can understand as an isomorphism of the zeroth homology group of your fiber. In higher dimensions, or rather for the case of surfaces, the monodromy, well, this is the definition that sticks. The monodromy will be given by some isomorphism of the one cycles of the fiber. There is still, if your projection is generic enough, there is still precisely one thimble per critical value. So in dimension 1, this was just a consequence of complex analysis. In higher dimensions, this is a result of Picard-Lefschetz theory. We could obtain all one cycles by gluing thimbles together, as I've mentioned in dimension 1. In higher dimensions, or rather in even dimensions, this is no longer the case. But we still obtain almost all the homology of the surface. What we are missing is something of rank precisely 2. And you can show that the periods on this this subset of the homology are actually 0. So for the sake of computing periods, you're not missing anything. And then finally, the reason for this construction is that this description of homology is explicit enough that we can compute the periods just as line integrals. So we can efficiently recover these numerical approximations of periods. How much time do I have left? Apology.
14
minutes.
Yes, yes.
Okay.
So the periods are 0, but the matrix is still invertible. The original matrix that was changing basis from the Rham homology.
So I will address this in, well, this slide actually, the next slide. One thing that I haven't mentioned at all is how you obtain this projection onto the projective line. And it turns out that if you're given just any surface, you can't do this directly. You have to do some blow up at some point. The reason is because the way you obtain this vibration is by taking a pencil of hyperplanes, and the fiber is going to be given by the intersection of your initial surface with one of these hyperplanes. In dimensions 1 and less, this is fine because you can make it so that the axis of the pencil, which is the intersection, well, the intersection of all these hyperplanes, avoids your initial variety. But in higher dimension, you cannot do this, and thus you will have some non-trivial intersection x prime with the axis of the hyperplane pencil. And so in every fiber, you will have a copy of this exceptional set x prime, and really what this means is that what you do when you consider this vibration instead of the initial variety is you've blown up the variety along this exceptional subset. And what we compute with this method is, in fact, not the homology of the initial surface, but the homology of the modification of this variety that I've called y, which is the blow-up of x at x prime. If we want to recover the periods of x, it requires a bit more work, but we have to be able to identify these homology classes that stem as exceptional divisors of this blow-up. But still we can do it, and then we can recover the exact period matrix of x. And to give you more details as to what these two additional cycles are, I represented them here. The fact is that you're missing two, so you're missing an n cycle, or a 2 cycle in the case of surfaces, of your fiber. So in the case of surfaces, it's just going to be the fundamental class of your fiber. And a section of the bundle of n-2 cycles of your fiber. So if you have a section, this might provide some class which cannot be represented by these connections of tubes, these sums of thimbles. Okay, and finally, the last technical thing I wanted to mention is how you compute the monodromy. So the way you do this is you assume you know everything about the fiber, which by induction you can. You assume that you know how to compute the cycles and the periods of your fiber. And the periods, as I've mentioned, give you this isomorphism between the homology and the algebraic theorem cohomology. And this is nice because in the homology side you have integral coordinates, and in the algebraic theorem cohomology you have some connection which stems from this vibration, namely the Gauss-Menin connection. And this means that if you can compute the differential operators that describe the deformation of the algebraic theorem cohomology, if you have the right dictionary to translate it, you can recover the monodromy on the homology, on the integral homology. And this dictionary I've mentioned is precisely the period matrix of the fiber. And I will make this concrete by showing you an example. So now I'm considering the Fermat cubic surface, which is defined by this polynomial here. The first step is computing this period of the fiber. So this is exactly the same thing as I've done before. This is just the periods of some algebraic curve. And so here is the matrix. Then I can compute, well, I choose some base point. I compute the critical values. I compute these simple loops. This is the same thing. And then I compute this differential operator, which represents the deformation of the fiber above a point as you move it in the complex plane here. And as you can see, it's quite a large operator. You wouldn't want to do any computation with it by hand, but a computer can still easily handle such an operator. And I can compute the action of monodromy on the solutions of this operator. So this is the action of monodromy on the cohomology that I've mentioned. So this should take 20 seconds, if I remember correctly. And in the end, you get this 2x2 matrix, of which the entries are also a priori transcendental. And here I've computed them with roughly 80 digits. And what I've been telling you is that this matrix also represents the action of monodromy on the homology. And the dictionary to understand in terms of integral coefficients is precisely the periods of the fiber, which means that if I compute the conjugation of this monodromy matrix by the period matrix of the fiber, I should get integer coefficients. And this is indeed what you find here, that up to 72 digits you recover 1 in these entries. And in fact, well, you know by the theory that these are integers, but since you've computed them with sufficient precision and rigorous error bounds, you can recover the exact action of monodromy on the homology of the fiber. And so you can do this on all the fibers, which might take some time. So you have 12, if I remember, yeah, you have 12 critical values, so you're computing 12 monodromy matrices, which will be the same, well, 2 by 2 matrices such as this one. Here they are. I mentioned that there was one thimble per critical value. This is something you can see because the border of the thimble is given by the monodromy of the starting cycle minus the initial cycle. So it's going to generate the image of this monodromy matrix minus the identity, and this is something you can see here. All of this has rank 1. And once you have these borders, you can do this gluing business still, and you can recover homology classes in the cubic surface, which are computed there. And then once you have this description of the homology in terms of the symbols, it's just about integrating the forms on these homology classes, which is what is being done here. So there are 6 forms to integrate on in total. It's already done 4. Maybe let me skip. So this would take roughly 2 minutes in total, but I'm just going to load the results. And in the end, you get this period matrix, which, as you can see, is not square. It's 6 by 10. But these are, so this is the period matrix of the homology classes of this modification, this blow-up of x at x prime, evaluated against the cohomology classes that come from the cubic surface. But as I've mentioned, you can, yeah, this exceptional set here is just the intersection of the initial cubic surface with the line. So it's just going to be 3 points. So you have 3 extra cycles in there, which is why you have 10 instead of 7. But you can get rid of these 3. You can identify them, which is what I was saying. And you can recover the sum, well, not the submatrix, but the actual periods of your cubic surface. And now, as you can see here, we go from 6 to 7. It's because this description of the cohomology that I've given you is not actually so the description of the cohomology in terms of these rational functions is not everything. There is one class that cannot be described as some residue of some rational function, and this is precisely the class that is missing here, which corresponds to the intersection products with the hyperplane class. And so in the end, you recover this 7 by 7 matrix, which is what you were after. OK, and now maybe let me share my last slide, which is just the resulting results of this method. So we were able to compute, well, with this method, we were able to compute the periods of quartic surfaces defined by generic polynomials in roughly an hour, which was previously unattainable with other methods. We were able to apply this to a specific example coming from physics, namely the tardigrade family, which corresponds to a family, well, which corresponds to this Feynman graph, and which of which the varieties associated to are singular quartic K3 surfaces, and doing this we can recover the Picard rank of this, well, the generic Picard rank of this family, and an embedding of this Picard rank into the standard K3 homology lattice. Something else we were able to do is find examples of polynomial equations defining quartic surfaces with a Picard rank, well, with any Picard rank. So this was a project that was started by Emre Sartos and Pierre Lerès with the algorithm of Emre Sartos. They tried finding sample equations for each possible pK rank, going from 1 to 21, and they were missing precisely these 3. And for instance, I think this one corresponds to a pK rank of 2. Sorry about that. And you can see that this has many monomials, which is why it was not attainable with the method of homology, but with our new method, we are able to compute the periods of such a quartic surface. As I mentioned, this is generalizable to other types of variety. More importantly, this case of elliptic surfaces, this has already been implemented. So if you have elliptic surfaces for which you want to compute the periods, well, the holomorphic periods, you can do this using this Lefschetz family package. And finally, let me just mention that the bottleneck for dealing with higher dimensional varieties and high degree varieties is still the size of the Picard-Fuchs operators. So what we've gained compared to Amos-Sartre's method is one step in this dimension case. So we are able to compute the periods of quartic surfaces, but if we want to compute the periods of quartic threefolds, we'll have to integrate the same order 21 and very large degree operators as the one Amos-Sartre needed for the case of quartic surfaces. So I think this is everything I wanted to say, so thank you very much for your attention. I'll be glad to answer any question you have.
Thank you very much. Some questions? Yes?
Actually, next question. Did you try to think about when you want to make classical integration for last variable? It's very complicated. To apply just dirty trick like double exponential method for function non-variable, one can calculate integrals of analytic functions again. With exponential precision, just by change of variables. You know, this double exponential methods. It's, if you have function of 0, 1, make change of variables to infinity, minus infinity to infinity with exponential decay, and then you just take sum of like replace Fourier transform, check sum of some arithmetic series, and it gives exponentially good precision for any analytic function.
And does it give rigorous error bounds?
Yes,
or yes, okay, that's interesting. I didn't know about this.
Yeah, it's completely non-algebraic. Yeah, but it's yeah.
Thank you very much for your.
You mentioned that you computed. You mentioned that you computed the Feynman diagrams. I presume it's for massless theory. What kind of a Feynman diagram did you compute, in fact?
The Feynman diagram is this one. So the paper was in general about two-loop Feynman diagrams.
But in what kind of a theory?
I'm not entirely sure. So my contribution was mostly this integration of periods.
Did I understand correctly that you had only 2 by 2 monodomy matrices?
So in the cases I've presented, yes.
Is there a reason for that? Why don't you have a longer cycle?
So the reason why I had 2 in the case of cubic surface is because the fiber is an elliptic curve, and the dimension, well, the dimension of the first homology group of an elliptic curve has rank 2, which is why we have 2. So we only have 2 cycles. But I think I might have an example somewhere.
It's not a general fact. It's just
no, not at all. For instance, for quartic surfaces. No, I don't have it here. But for quartic surfaces, you would get 6 by 6 matrices because the fiber is a degree 4 curve, which has genus 3, and so the first homology rank, the first homology group would have rank 6.
Other questions, remarks, comments? We thank the speaker again.
Thank you very much.